right, everyone. Welcome to another edition of CS 340. I'm your host, Frank. Payman is your co-host. I see Kihong has got is looking at the printed out slides, not the hidden slides. So we'll address that. The course schedule is right on the syllabus. Okay, so today we're going to talk about ensemble methods. Last time we talked about K-nearest neighbors, where basically it's like a super simple classification algorithm as different from K-means, which we'll talk about later, which is a clustering algorithm, unsupervised method. So K-nearest neighbors, the way you classify a test data point x total I is you just go into your training data set and find the K, that's the K-nearest, the part of K-nearest values of x that are most similar in feature space. So your query is x total I, xi's are your data, and we looked at these examples last time where their query example comes in and we just look to see which of the data items that are closest in feature space, and you use the mode of the corresponding labels and make that prediction. We called it lazy learning because the model, the source code of the model actually has to have that your training data in it, x's and y's, right? This means that K-nearest neighbors is an example of a non-parametric model, where in this course we define non-parametric to be a model whose size grows within. The number of examples grows, so the source code of the model grows, so blah, blah, blah. And we didn't prove it, but there are some very nice properties of non-parametric models, in particular K-nearest neighbors, with respect to test error in the limit of infinite data. But K-nearest neighbors suffers from very high prediction cost because you need to look through all of your training examples to compute distances, and due to the curse of dimensionality, right? Distances grow as the dimension of the space grows, which means that to find actually truly nearby examples, in other words, to have a decision surface that reflects the true data distribution in a high dimensional feature space, you might need a very, very large number of examples to actually populate the space, such that you get counts for each subdivision of the space, or more to the point, so that the decision surface is reflective of the actual discrimination boundary between classes in the high dimensional feature space. We started talking about norms as well, and we sort of implicitly introduced some notation. A common way to define the distance between a couple of examples, right here again, is to take the norm of the difference between the feature vectors. Okay, so if xi here is a training example and x twiddle I twiddle is a test example, right? We talked about the norm notation, and we said that the default norm is 2, but this will be the L2 norm here, whose definition is given here. It's the square root of the sum over the dimensions of the feature vector of the difference between the feature vector values squared. Okay. This norms in general are ways to measure lengths of the vector. And just to be 100% critical, although I do this on another slide in the future, right? If this is xi and this is x twiddle I twiddle, right? What we're looking for is the length of this guy, right? That's how close those vectors are in vector space, in feature space, right? So the norm of that vector is the thing we're after, right? And we want the length of that vector to tell how close these two items are to one another. The most common is the L2 norm, or the Euclidean norm, where this vector R, doesn't matter which direction it goes, but this vector R, the norm of that is the sum of all of the dimension elements squared square root of that, right? And that corresponds to your standard notion of Euclidean distance, right? There's an entire spectrum of norms, but the 3 most common norms, the ones that we'll discuss in this course, are the L2 norm, the L1 norm, and the L infinity norm. And we'll go through these in 2 dimensions and then move up to D dimensions, and it should be relatively clear what's going on. So the L2 norm, or Euclidean norm, again, think of this R as the difference between 2 feature vectors. That's what we're going to be thinking about. But for now, it's just some vector R, and it happens to be R as R1, R2. It's a vector with 2 dimensions. We're label it R1, R2. The Euclidean norm is just R1 squared plus R2 squared square root of that, right? So if this is the vector R, and again, this might be R1 and this might be R2, we're just plotting the vector in this vector space, then the 2 norm, the length of the vector R corresponding to the 2 norm is the length in the Euclidean distance in the Euclidean sense. Square roots, it's, you know, this squared, square root, added together square root. The L1 norm is the Manhattan norm. So same vector R, the L1 norm is defined as the sum of the absolute values of the dimensions of the vector, period. Okay, so note there's a 1 here, so this is the L1 norm, and this is the definition in 2 dimensions. And the reason why it's called the Manhattan norm is basically it says what the distance is, or the length of this vector is in some sort of different units, and we can think of these as blocks you would have to walk. So if you have to walk in order to get from the origin to the end of R, you need to walk, you know, 1, 2, 3 blocks in this direction, and then 1, 2 in this direction, right? Then the Manhattan norm, or the L1 norm length of this vector is 5, because it's 3 blocks in one direction, 2 blocks in the other direction, 5 total blocks. The L infinity norm is the max norm. Says basically just take the max of the absolute value over all the dimensions of the vector. Okay, so in this particular case, R2 is the longest or largest component of the vector in absolute magnitude sense, so that's the infinity norm. Okay, and based on these definitions, it should be really straightforward to generalize this to d dimensions, right? So the definitions of these norms in d dimensions looks like this. The L2 norm, you just sum over all d dimensions of the value of that dimension squared, take the square root of the whole thing. The L1 norm, again, you just sum over all d entries in the vector of the absolute value of the entry of that vector. And then the L infinity norm is just the maximum over all of the entries in the vector of the absolute values of the dimensions of each vector. Okay, cool. So we have norm and then norm raised to a power notation, and you should memorize this, in particular the thing that comes at the end of this slide. So we often, as I've warned you already, leave out the 2 for the 2 norm. In other words, we'll just leave this blank when we mean 2 norm, right? We use superscripts for raising norms to powers, right? So the 2 norm squared is a thing that we're going to see a lot, particularly when we do least squares or linear regression or these sorts of things. And this means take the value of the norm and square it. But you should definitely work through this. If this is not immediately obvious and straightforward when you see this, then you should definitely take the time to work through this on your own. All of the following quantities are equal, right? So we have the default norm, which is the 2 norm squared. We've plugged in the value, so that's the 2 norm squared, is the value of the 2 norm squared. If we plug in the definition of the 2 norm, we have the square root of the sum over all the dimensions of the values of the dimension, each dimension squared, square root of that. You notice that the square roots cancel, so that means that the square root and squared cancel, so we have the sum of the individual elements squared. This is why this 2 norm squared is the sum of squares. This is the same thing as just summing over the dimension, multiplying the values in each element of the vector together. And that is the same thing as taking the inner product between the vector with itself, right? And that's basically a dot product between R and itself, right? If you think about it, this is, you know, if we have R1 and R2 like this, that's the transpose, because R1 and R2 is like this. Then when you do the matrix, when you do this matrix multiply, you get R1 squared plus R2 squared, okay? And we'll equivalently denote this inner product or vector multiply or inner product between the vector as being like this, basically a dot product, right? So I've already hinted at this, but norms as measure of distance works like this, right? Basically, by taking the norm of the difference between 2 vectors, you get a distance between the vectors, right? So if we have R and S, and we look at the difference between the 2, that's going to be this vector right here. and we want the length of that. Fine, I guess we've already got it right there. Beautiful. So the norm, the 2 norm of r minus s is a Euclidean distance between r and s, right? The 1 norm is the number of blocks. It's the L1 distance between r and s. It's the number of blocks you need to walk to get from r to s. And then the max is the most number of blocks in any direction you would have to walk, okay? So the point of this is going to show up in several different places during the course. These different norms place different weights on different kinds of differences, right? So if I diagram some, and you'll see a diagram like this later, if I diagram some 2 different vectors, r and s, and these are the individual heights of the, or the values in the entries of these guys, the distances between these 2 vectors, what we use to say, for instance, there's like one vector here, so this is like r, s, t. And this is r1, r2, these are the values. Okay, so the distances that we compute between these vectors, the numbers that we use to compute what's nearest neighbor, what is a nearest neighbor, are going to be different depending on the norm that we utilize, right? So the point is that here, when we're computing distances between vectors, when we look in every dimension, the differences are basically the same. Like there's no difference between a large difference or a small difference. They're all treated exactly the same, right? But in L2, if any one of these dimensions has a large discrepancy in value, then that is going to mean that these vectors are, the distance between these vectors is computed as being very, very large. It ends up being very, very large, right? Because the difference gets squared, okay? So, and of course, you know, with L infinity, the infinity norm, the biggest difference is the only one that's important, okay? So in the context of k-means, which we're talking about right now, I mean, k-nearest neighbors, excuse me, the notion of what are your neighbors, like actually which data points are assigned as your neighbors, will be different depending on the norm. And that corresponds to how different individual dimensions of the feature space are treated. Like large differences in any one dimension could end up meaning that 2 vectors that are otherwise extremely similar end up not being neighbors, simply because there's one element of the vector that's widely divergent. Whereas the L1 norm is less sensitive to this. And this is going to show up in a couple of different cases, in particular when we're doing regression, and these are differences between our prediction and the true data. So we hinted at this, I hinted at this as well before, k-nearest neighbors, and in fact, most machine learning methods, you get to choose the distance function that you use, right? So the most common k-nearest neighbors distance function is just the norm of the difference between vectors, right? And you can choose between L1, L2, L infinity norm, whatever. And you can think of these as, hyperparameters or model selection choices that you might want to make. You know, k-nearest neighbors with L1 norm. Great, awesome, right? And of course, and we already talked about this, this relates to sort of normalizing the features so that they all live in the same unit or something like that. But you can also think of it as actually just being a weighted norm. And that's kind of the same deal. So if you have a weight for each feature dimension, you can have some kind of weighted norm. There are also ways to take into account correlations between features. So in other words, if you compute the covariance matrix between all of your features and use that when computing distances between vectors, the Mahalanobis distance is the way you do this, right? And we already hinted, because I couldn't remember the Jacquard index or Jacquard similarity before, intersection over union of sets. If xi's represent sets, you might want to compute distances by Jacquard similarity, or edit distances if the xi's are actually strings, or the branch of machine learning that tries to learn the distance metric. In other words, basically this function instead of the norm, you can think of this as some parametric form that we want to learn somehow, right? can learn this distance function as well as your classifier parameters, whatever that happens to be. Okay, cool. So we're in pretty good shape at this point. We've actually covered a fairly surprising amount of ground for where we are in the course, if you think about it, right? Like we kind of start slow, but we're slowly accreting some pretty impressive skills. So we have, decision stumps, right? But really, who cares about those, because we've got decision trees, right? And we know that this is the form of the decision tree. It's like, this branching if then else thing where you learn the labels, the values, and the features through some sort of greedy algorithm. We have naive Bayes, where you use a generative model to decide whether the probability of a particular data set under each classification condition is greater than the others, and you make a factorization assumption when you're learning the parameters of this model, which basically mean estimating each of these conditional probabilities. And now we have k-nearest neighbors, where if we want to classify this feature vector, we can look through the data and find here the k equals 1 nearest feature vector, and then take the median of all the k nearest neighbors and make a prediction. So cool, we have 3, arguably 4 if you count stumps, different machine learning models already under our belt, and they're pretty powerful. You can actually do a lot with all of them. Okay. So cool. Let's think of some other examples of we're going to talk about a couple other examples of supervised learning, just to sort of continue to crystallize in your head how you can express problems as supervised learning problems. In addition, we can think about ways to sort of help with the cursive dimensionality. Okay, so let's think. Okay, we want to do OCR, and let's pretend that we have a system that actually automatically extracts bounding box regions around individual characters in a document. Okay, doing that by itself is a hard problem, but let's assume that we have that. But once we have the bounding box, we have an image of a character here. These are only numeric images. And what we like to do is we like to be able to go from that to a particular digit ID. So, this is an image of 8, its class label is 8. This is an image of a 1, its class label is 1. Okay, something like that. Okay. So first of all, how do we actually do this? All right. Well, the supervised learning problem is we take an image or all some featurization of this image and predict a label for it, right? And one way to do this is to basically construct your data matrix by extracting the grayscale intensity. We talked about this. We extract the grayscale, or here black and white, doesn't really matter, intensity of every pixel in the image. So there's this, and then there's this, and there's this. And if we have 28 by 28, I think it's 784, I think is the total size of the feature space, right? And we have a label for each of them. This is not binary, but instead there's 10 different character classes here. That's fine. Okay, so we can apply any of our techniques to this so far, right? We could apply naive Bayes to this, particularly if these are just binary feature values, right? We can do k-nearest neighbors, we can do decision trees, we can do whatever, but it's worth sort of introducing a couple of things we're going to think about throughout the course here, right? So, and the way we'll think about we'll introduce the concept is to think about k-nearest neighbors for this application, where let's say, for instance, we have a query image and we'd like to actually decide what character it is a picture of, right? And one way we could do this is to just look in feature space, whatever that happens to be, right? Compute some sort of distance using a norm between the examples or like whatever, and then return the mode of the class. That's exactly what k-nearest neighbors would do. But now we have a 784 dimensional space, so distance is going to be pretty large, and this might not be, well, there's a couple of things to talk about here. So first of all, just to make it super clear, right, what we see and what a machine learning algorithm sees are pretty radically different, right? So what we see is that, right? We look at that and we say, that's a 3. To the computer, it's just some, ones and zeros or grayscale values in a matrix. And in fact, actually what the computer gets is this vector, right? Which when you look at this and actually think about what machine learning is doing, it's kind of amazing that we're able to do anything really, actually, right? Because this is the space in which we're working. So we've got, that thing lives in R to the 768 or whatever, 86, whatever, something like that. R to the approximately 768. So there's a little comment, a snarky comment on the channel, which is, what is this, machine learning for ants? Yeah, but just think about it for a second. This is actually what your machine learning model gets, right? Okay, cool. So if that's what you get, are these two images similar? Payment, are these two images similar?
Sorry?
No cheating, don't click ahead. Are these?
They look similar, yeah. Probably the same, the one on the right is a little bit, shifted, but they look similar.
So they're certainly similar in the sense that you would classify, that you would classify them as a 3. Keep on with questions. There's some questions coming in. So is KNN for MNIST the sum of per pixel distances, like comparing the intensity between 128 image 1 and 128 image 2, and then the sum of all pixel differences? Yes, that's correct. Yeah. So the question is, are these two images similar, right? And for those of you who, for the people who already know that this is MNIST, great. The answer is probably fairly obvious. But for a large number of you, notably, you will not necessarily have thought about this before, which is to say that these things, if you actually just compute the difference, right? If you think of this as a vector living in a 768 dimensional space, and this one as living in the same space, and then we take the difference of those vectors and then smash it back into an image, the difference is actually very, very large from the computer perception point of view, right? The computer doesn't know that if you shift the 3 down ever so slightly, it remains exactly the same, right? From a classification perspective, you shouldn't change the class, right? In other words, KNN's Neighbours or whatever algorithm you apply here doesn't necessarily know, and why would it know that the label should be translation invariant, okay? Another perspective on this is that, right, by the distance function in KNN's Neighbours should be such that translations don't result in large distances between examples. Right? So the question is, will KNN work on this despite the large differences? Thank you, HAL 9000. And the answer is not particularly well right off the bat. It actually won't be terrible, but it's not going to be state of the art, that's for sure. But one thing, like an engineering thing that we want to think about, which is deeper than that because it addresses distances, it addresses the cursive dimensionality explicitly, so on and so forth. What we want is we want our models to compute distances or assign labels in a way that's invariant to transformations of the feature space that to a human labeler would not result in changes to the label. So that's what we mean by we might want the classifier to be invariant to certain feature transformations like translations, rotations, or changes in size or mild warping. So the hard way is to think about how could I possibly define some sort of distance function between xi and x twiddle, I twiddle, right? How could I possibly design such a function in a way that is translation invariant, right? Like that it returns the same value, 6, if xi or rather, I guess the test image is translated all around, right? That's really hard, right? It's really hard. The easy way, the fast way, is just to add transformed data to your training data set, right? And this sounds really dumb, and it is kind of dumb, but it works really, really well, and it's super important for all kinds of applications, right? So in particular for computer vision, right? One thing that you can do is, you know that the label of this is 3, you know that the label of this is 3, you know that the label of this is 3, and you know that the label of this is 3. And in fact, you know that basically any translated, slightly rotated, slightly resized, or slightly warped version of the exact same training image is still going to be labeled a 3. So we can do data set augmentation in order to partially address the cursive dimensionality, which is really kind of the same thing as making filling up the space so that nearest neighbors are more likely to be found with the correct label. Okay.
Did you try and censor the mass of the image?
In principle, yes, but then you have to figure out how to scale, how to rotate, how to so on and so forth. So yes, one of the things that's a characteristic of well-formed data sets and the kind of data pre-processing that we do is that indeed the digits probably should be centered, but even then there will be small variations that the training data won't have. So you'll want to augment the training data so that you have better coverage and your model generalizes better. Yeah, I mean, there are issues with all of these things. If you're interested in like permutation or other kinds of invariant neural network architectures, and you want to sort of think more deeply about this, one of the world experts on this is in the stats department here. His name is Benjamin Bloom-Reddy. He's does some very interesting research. We work together for a amount. So anyway, cool. Let's think about another application. Payment. Let's build a Microsoft Kinect body part pose classifier.
Okay.
And we're not going to do laser because, you know, that's not what it is. We'll do it from IR. That's fine, right? And what we want to be able to do is we want to do a 31-way pixel classification to classify these pixels as being the right hand and these pixels as being the left face, and you know, these pixels as being the right, whatever this is, right? So how do we do this? How do we set this up as a supervised learning problem?
We have to. Do we have the ground truth data? Like we have to label the image. Which part is what? Right? Which part is right hand, left.
Yes. So we need some supervised data, right? So the first thing we need to do is we need to collect hundreds of thousands of labeled images, right? We can do this. We get a bunch of different people to dance, and we hire a bunch of people to label that data very painstakingly by, you know, drawing in Microsoft Paint or whatever. And we want to do this for a variety of people types, right? And image types. We can also do the same kind of, we can do this simulated training data, right? Where if we build a simulator that generates body poses and then render those, we can get both the depths, which is this grayscale. That's the image. That's like how deep each pixel is, and the corresponding label. Okay, great. That's cool. And then in order to really set this up, we have to figure out what features we're going to use, because it's not going to be enough to just look at the depth of one pixel value and try to predict what body part it is from one pixel value. We need to extract some information from around that pixel, right? so that we can build a feature vector associated with that surround that we can use to predict this pixel value, right? So we need to extract some features that are cheap enough to do to extract in real time, like things like depth differences between pixels and nearby pixels. And then we can treat classifying each body part as a supervised learning problem. Yeah? Cool with that? Good. Then if you have a GPU and you're running on a Xbox, right, then you can run the classifier in parallel on all the pixels using a GPU, for instance. And of course, as always, all these steps are important, but we're going to focus on the learning step. And the question is, out of our stable of classifiers, do we have any classifiers that are both very accurate and run in real time?
Decision tree is not accurate, super accurate, right?
Decision tree isn't super accurate, right? It tends to overfit, so you have to keep it, you know, you have to limit the depth, and then it's not super accurate. KNN's Neighbours, as HAL 9000 said, is not fast, right? Because you have to look at all the training data, so it's going to be really, really slow. And what other, so decision trees, or decision tree, naive Bayes. Yeah, it's not super obvious how yeah, okay. So decision tree not super accurate. Naive Bayes not so obvious how that it's gonna work here. And it's not necessarily that fast unless you have a huge number of features, and we're kind of limited in the number of features that we can use for this because we want it to be super fast, right? So this system actually worked using an ensemble method called random forests, okay? And this is one of the sort of, yeah, we're finally there. We're going to go from decision trees to random forests, and random forests are kind of like a go-to. You just got to try it. It usually works really well. Super powerful machine learning method, generic machine learning method. And the way we're going to do random forests is to just explain how you get to a random forest, because they seem a little bit magical when you think about them, but they're actually really not, right? They're just a method for ensembling weak classifiers that make relatively independent errors, okay? But let's talk about ensembling in general first. So ensembling methods are methods that for classification that consume classifier output as their inputs, okay? It used to be called meta learning. Don't look at meta learning now because meta learning is completely different now. And ensemble methods do have some of the best names in machine learning: averaging, boosting, bootstrapping, bagging, cascading, random forest, stacking, so on and so forth. The point is that ensembling and ensemble methods often have higher accuracy than the input classifiers, okay? And if you remember the fundamental trade-off that we talked about, which is like how small can you make the training error versus how well the training error approximates the test error, the goal of ensemble methods is that the meta classifier, or the ensemble, does much better on one of these than in the individual classifiers, and it doesn't do too much worse on the other. Now, there are a couple of ways of ensembling classifiers that come to mind right away, right? One is boosting, which takes weak classifiers, in other words, classifiers with high training error, right? And ensembles them in a way that results in much lower training error and at the same time, ideally, better approximation or generalization, right? Averaging, which is what we're going to actually talk about and cover in this course. So boosting, an example of that would be like ADA booster or something like that, right? Or even XG boost, which I think we don't cover, maybe we do, I don't remember. Averaging improves the approximation error of classifiers with high approximation error, which is to say, if you have a model that kind of overfits a little bit and makes errors on test data, right? If you have a bunch of models that are a little bit too strong but are pretty good, but they make independent errors, we can average them in a way that ends up resulting in an ensembled classifier that does well. And that's exactly what random forest is, and that's exactly what the Xbox Kinect used in order to do real-time body part identification, okay? And we're going to get to random forest, which you're also going to implement and play with multiple times throughout this course. So the input to an averaging ensemble method is the predictions of a set of models, right? So for instance, you have some classification task, supervised learning task, and you train a decision tree, a naive Bayes classifier, and a k nearest neighbors classifier, and you use each of them, the trained models, to make a prediction. Simple model averaging just says, okay, run each of these pre-trained or trained models, the decision tree, the naive Bayes model, the k nearest neighbors model, and take the mode of the prediction. So decision tree for the email example produces not spam, the other two produce spam, the mode of that is spam, great, okay? So another thing that you can do, which is arguably even more powerful, is that you can stack your regressors, okay? So what you do here is you fit a classifier that uses the predictions from the other classifiers as features. So same setup, we train a decision tree, a naive Bayes classifier, and a k nearest neighbors classifier to classify email as spam or not spam, right? The outputs of those, so you basically, run these through, and then you train another classifier starting from this as your data to predict spam or not, right? So there's another decision tree at depth 2, so on and so forth, that gets data, which are the labels of all of the items provided by the different classifiers, and the true label, and tries to learn how to.
So you only need KNN during the training phase?
That's a good question, Ramon. Thank you for bringing it to my attention, Payman. So no, at test time, you would still put in a test input here, and each of these would classify it to produce some, vote from each of them: spam, not spam, spam, not spam. Okay, and then this decision tree is run with those to make a final prediction. If you're stacking, how different models would you need, or would you run different versions of the same model? Thank you, Hal, for that. So this is another one of these who knows questions, right? How many different models? Well, this is a hyperparameter, right? Maybe one model, if one of them is dominant and always is better than the others, and the errors are perfectly correlated. If the errors are not perfectly correlated, then more is probably better. It's something that you would have to choose via model selection, via cross-validation, or something like that. So averaging or stacking often performs better than individual models, basically almost always, and it's used by Kaggle winners. So if you're going to do Kaggle competitions, you should definitely know about ensembling. And the original Netflix classification challenge, the user rating competition, was stack classifier, the winner. So just a little digression to make it clear why or how averaging can work. So if we have 3 binary classifiers, and this is the important word here, each independently correct with probability 0.8, with simple averaging, that means, i.e. basically taking the mode or the majority vote, the ensemble classifier is correct if we have at least 2 right.
Why would you use KNN if it's too slow?
Good question. We're not talking about speed right now. We're talking about accuracy. So indeed, the ensemble method would be slow. The speed of the ensemble method would be no faster than the slowest method, right? But we're building towards random forests where all of the things that we're going to ensemble are in the same family of model, okay? So with simple averaging, the ensemble is correct if we have at least 2 right. So if we make independent errors, then the probability of all 3 classifiers being right is 0.8 cubed, okay? So the point is that, classifier 1 is right, 1 is right, probability 2 is right, so on and so forth, probability 3 is right. We can only say that this is equal to this if we make the assumption that the classification output by each of the classifiers is independently distributed. But averaging still works well if they're approximately independently distributed, which is what random forests do. So the probability of 2 rights and 1 wrong, there are 3 different ways to have 2 rights, and 1 wrong, and then this is the probability. 2 being right, 1 being wrong, that's it, okay? So you can already see if you add these together that the probability of being right in an averaging model where each of the individual classifiers has this accuracy and that they make independent predictions is greater than 0.8. So we've won, okay? So the ensemble is right with probability 0.896, right? Great. And I've already stressed this, it's important, so it's worth re-stressing again. So for averaging to work, the classifiers need to be at least somewhat independent, okay? And we're going to build random forests in such a way that we make the classifiers somewhat independent. Same basic what they need to be. Okay, yeah, so Nico, this is a good question, which is basically, do they need to be different classifiers? You can ensemble different classifiers, and that's likely to lead to uncorrelated errors because they make different sort of assumptions about the structure of the input-output relationship, the regression or classification relationship. But no, in fact, random forests are ensembled decision trees, okay? Obviously, you want the probability of being right to be greater than 0.5. Just as a note, if you ever have a classifier that is right only with probability 0.2, then just switch the labels and you have a classifier that's right with probability 0.8. And the probabilities also shouldn't be so different. Otherwise, you might just take the best classifier and say, you know, screw the ensembling, okay? So let's go back to the email example. We're classifying spam or not spam. We have 10 classifiers. They make this. If these independently get 80% accuracy, then the mode, if you choose the mode of the classifier output, the performance of this classifier will be very, very close to 100%. Now, of course, it's not exact and blah, 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 because the errors made by the classifiers aren't perfectly independent usually. So why and when can averaging work? Why can averaging lead to better results? Well, think about deep decision trees, or like not super deep, not all the way, but relatively deep, right? They probably are going to overfit, or they have the capacity to overfit, right? If you train the exact same tree, there's no averaging that could possibly work because they have exactly the same model structure, they make exactly the same decision, so there's going to be nothing that comes from averaging. But if you modify the trees in a nice way such that they make independent errors, right, then the probability that the average is wrong can be lower than that for each individual classifier, right? Which is to say, the average basically pays less attention to the specific overfitting of each classifier. And this is really what's going on in random forests, okay? So random forests average a set of deep or deep-ish decision trees, okay? And they tend to be one of the best out-of-the-box classifiers. So if you're doing practical applied machine learning, one of the things that you should do is, you know, do all your data munging and whatever, plot your features, figure out what's going on, and then dial up sklearn and apply a random forest classifier. Well before neural networks, well before anything else, especially if you have relatively small n, random forests are very hard to beat. Yeah. So, and predictions are fast, which means that we can use them in examples like the Xbox Kinect, okay? The problem is, of course, that if you're thinking about how to do this, right, do deep decision trees make independent errors? No, not if you train them on the same data. You get the exact same decision tree, right? So there are two ingredients on top of what we've talked about right now in order to make random forests, and then you understand random forests, okay? One is bootstrapping, the other one are random trees, okay? And they're related to one another. So for those of you who are not familiar with what a bootstrap sample is, we're just going to do it by example, and then it's sort of obvious what it is. So let's start with a standard deck of 52 cards, okay? To draw a bootstrap sample, here's the procedure. Sample a random card, put it back in the deck, shuffle. So you're getting independent draws from this deck of cards. Pick a random card, put it back in the deck, reshuffle. Remember this value, so on and so forth, right? Pick a random card, put it back in the deck, reshuffle, okay? At the end, you will have drawn 52 cards, Okay? And you're going to remember their suits, values, and so on and so forth. And that is going to result in a data set with 52 elements, which looks a lot like the data set above, but will have some cards repeated, some cards missed, so on and so forth. Okay. Cool. So each one of these new decks, which you sample with this procedure, is a Bootstrap sample. Clear enough? Okay. So each one of them is a Bootstrap sample. Some cards will be missing, some will be duplicated. The calculations, whatever calculations you do, fit a tree, compute some sort of statistics, so on and so forth, they'll be similar, but different than the original data. And that's really important, right? So if you, like, for instance, do something silly like count the number of tens in this Bootstrap sample, it's going to vary from one Bootstrap sample to the next. But in expectation, it'll be 4. Same for aces, so on and so forth. So the Bootstrap sample maintains some rough trends, like 25% of the cards will be diamonds. The face card percentages will be right, and they'll be roughly 4, 10 cards, so on and so forth. The common use is when you're doing frequentist statistics and you want to get some idea of what your sampling, what the sampling distribution of your estimator will be. If you don't have independent data sets, then you can do a Bootstrap sample and get a sampling distribution for your estimator and get Bootstrap confidence intervals and these sorts of things. That's the typical use for Bootstrap sampling.
How is this different from just adding some fuzz to our data?
That's an awesome question. Thank you, Dominic. Well, I would say it's different in one key respect, which is adding fuzz to our data is not clear. This is at least a clear procedure. There are some very deep technical results about Bootstrap sampling, which we're not going to go into here. I think what we can do in this course is say that Bootstrap sampling, in particular when combined with fitting decision trees, results in ensembles that generally perform well in the form of random forests. That's basically what we're going to say, right? In some sense, it is just fuzzing the data, but like, how are you going to fuzz the data? You shouldn't change the values, right? You don't want to change the difficulty here is when we're Bootstrap sampling our data, we have the input-output pairs. So there's lots of ways to fuzz the data. You can fuzz the inputs, you can fuzz the outputs. You don't want to do that because that's going to destroy the relationship. What you want to do is somehow change the population distribution. And it's not clear what to do besides this kind of Bootstrap sampling. You could subdivide the data, you could do cross-validated things, you could do stratified sampling, you could do that sort of thing, but you have your data and you want to produce different, relatively uncorrelated trees or relatively uncorrelated classifiers for an ensemble. Okay, so the first ingredient of random forests, we're almost to the end of random forests, is the Bootstrap. Basically, you Bootstrap sample a list of n examples, okay? So you choose a new set of training instances of size n independently with replacement, right? So yeah, for I equals 1 to n, sample a value between 1 and n, and you build your Bootstrap sample by picking the jth item and then making it the ith item in your new data set, right? This gives us a new data set of n examples, some duplicated, some missing, right? And just for the fun of it, for large n, the limit is approximately 63% of the original examples will be included, right? Then the next part of random forest, and basically we're done after this, is called bagging, where you use the Bootstrap samples for ensemble learning. So basically you generate several Bootstrap samples of the examples. So you have Bootstrap samples of size n, for instance, right? And you fit a classifier to each Bootstrap sample. In particular, you fit a depth-constrained decision tree to each Bootstrap sample. And then at test time, you average the predictions. Okay? That's a random forest. Okay? So it's an averaged ensemble of deep-ish decision trees fit on Bootstrap samples of your training data. Cool. That's it. Almost in time. So some key things that we talked about today are encouraging invariance or populating your feature space with more examples by transforming your data such that your classifier becomes invariant to transformations that you care about, like, or don't care about, like translations, rotations, scales, warps, that sort of thing in images, and similar things in other perceptual domains. We talked about ensembling just now, right? Which tries to basically generate models that generalize better, have better classification accuracy by, you know, combining classifiers or like using classifiers as inputs to other classifiers, right? And we specifically talked about averaging, which improves predictions of multiple classifiers if the errors are independent. And we talked about bagging, which is an ensemble method where we apply the same classifier to bootstrap samples. And that's exactly what random forests are. And next time we talk about unsupervised learning. So, okay, cool. Questions?
So we're essentially just taking many subsets of a data, taking different classifiers and training on different classifiers on them and averaging. How does this increase the accuracy?
So this goes back to the averaging slides. This is the fundamental question, right? It goes back to the averaging slide that we looked at, where if the errors made by, if each individual classifier is pretty good and the errors that they make are roughly independent, then the ensemble can be better. It won't always be better, but it can be better, right? And then the next question is, in random forests, how independent are the trees? They're not fully independent. Like, that's part of why we had the waffling language about, you know, being absolutely perfectly independent or fully independent, because the bootstrap samples are clearly correlated. They're conditionally dependent on the data, right? But what ends up happening is the bootstrap samples cause, under the greedy tree fitting algorithm we have, they cause two things to happen. One, they cause the tree structure to change, but also because of the duplication and omission of various data items, it means that the counts that actually happen in the leaves of those trees are also different, which means that the predictions that you make for out of sample or general, you know, out of sample data, right, the test data, are going to be different between the trees, right? Most of the time you'll be right, but the errors that you make are going to be different, and it depends on where you get sorted down into the tree in each of the trees in the forest, and what counts actually survived under the bootstrap sample that ended up in the same thing. So the exact same data item can be classified, you know, many, many different ways in the tree, and those trees are independent enough that if you have a large collection of them, average accuracy usually goes up. By depth constrained trees, do we set a specific fixed height of all trees? If so, how do we choose this height? So there are different versions of random forests. Typically, typically there's a depth that's pre-specified, or you decide to stop splitting the tree on some information gain threshold. And the trees don't necessarily have to be balanced. They can be unbalanced trees. There's all sorts of ways to do it. That's why we're talking about ensembling in general. But in general, you could say depth 10 tree, or you can say unbalanced tree with splitting stopped at a certain information gain threshold, or whatever. There's lots and lots of ways to implement random trees, random forests. What was the best solution for the OCR example to use K-nearest neighbors with transform training data? Thank you, Sean. Good question. The point of the K-nearest of the OCR example is to get you to think about distances in feature space and what feature vectors really mean, and the fact that in order to compute what's near, you may need to fill up your feature space with more examples that reflect the kind of transformations you would like to be invariant to. That does not mean that the best method is KNN with transform feature transform training data. You will, with very high probability, work on some advanced methods for this, like convolutional neural networks that we'll talk about later, that are very, very good at solving this problem, much better than K-nearest neighbors, mostly because the feature space they use is learned. So bootstrapping is better than training K-trees on K partitions of the data. I believe empirically, the test of time has suggested that that is indeed true, yes. Yes, yeah, almost certainly, yeah. Yeah, exactly. Elias has the right idea because you get to keep all the data. That's right. That's very interesting. I have no idea what you're referring to, HAL 9000, but you're welcome. So all the models are still getting trained on the same set of data. So that's the, okay, so that's good, Hakeem, thank you for asking this question. No, the models are not getting trained on the same set of data. That's the whole point of a bootstrap sample. The training data for each of the models is different, and it's the bootstrap samples that they're getting trained on, right? So it's definitely not the same set of data. The bootstrap samples are drawn conditioned on the same set of data, but the training data sets for each of the ensemble methods is different in random forest. My monitors are flicking in and out of life, so okay, there we go. How do we go about tuning hyperparameters for all the models in a random forest? So generally speaking, you assume that you restrict your random forest to be parameterized by a small number of things, like for instance, the information gain threshold, the number of trees, perhaps the depth of the trees, that sort of thing. Perhaps if you do subsample the data in addition to doing a bootstrap, the ratio of the subsampled set size to the full data, and you do hyperparameter search in that parameterized space. So there's a small number of possible random forests, or small-ish number of possible random forests that you would consider. So Kevin, I don't know which slides you're looking at, but the slides that I gave today have no mention at all of a homework due date. I think possibly there's a bad version online, and I'll double check. I thought that this got sorted, but I'll double check afterwards. So check the schedule on the course website to make sure that we have the assignment due date correct. Lex, is the purpose of using Bootstrap sample to avoid overfitting? No, the purpose of the Bootstrap sample is to ensure that each of the individual trees has a different data set and thereby makes independent or roughly uncorrelated errors in predicting on the test set. More questions? The term random forest only used in the classifier used to test Bootstrap samples is a decision tree, or is Bootstrap data trained on any other model? No. Yeah, so Mallory, good question. Yeah, so when we say random forest, we mean Bootstrap bagging, decision tree. So it's decision trees inside the random forest. Oh, I mean, that would be a random collection of machine learning models instead of random forest trees. There's a relation. Yeah. A situation use Bootstrap sample sizes larger or smaller than in, like smaller. Christopher, yeah, I sort of hinted at that in one of my questions, and I think you're picking up on this. Using a Bootstrap sample larger than in, probably not a good idea. You're not gaining anything from that. But definitely smaller is something that you do, particularly when in is very large. Yes, for sure. Yeah. So for decision trees, we pick the depth and minimize overfitting. I'm not clear about how we choose the depth of decision trees for a random forest. Roshan, great. I think I understand your question. So if I say that the random forest has 500 trees, and you're going to use bootstrap sampling of size n, right? Then the only hyperparameter left is the depth of the tree of all of the trees. So the cross-validation technique for choosing the right depth of the tree for a random forest classifier, that procedure is exactly the same as the procedure that you would use to select the depth in a decision tree. You train on a fold, on some number of folds, and test on the remaining fold, and then compute held out accuracy as a proxy for test accuracy, validation accuracy for as an estimate of test accuracy, and you decide on the depth of all the trees in the random forest simultaneously. You can also parameterize a random forest by, for instance, the information gain threshold, and just choose some quantized number of information gain values or something like that. Phew, okay. I think we're good. I'll leave it there. Thank you very much, Raymond.
Thank you.
Leave it for me. Okay. Thank you all.